In the last lecture, we saw that stars are giant nuclear fusion reactors that convert the mass of hydrogen to energy. It turns out that mass is perhaps the most critical factor in understanding the behavior of stars. Big, massive stars burn faster and brighter than smaller, less massive stars. In this lecture, it's the 30th of our series. I want to show you the evidence that the life cycle of a star depends on its mass. I have two main objectives in this lecture. First, after reviewing the last lecture, I'll begin by examining our own star, the Sun, in some detail. I want to give you a feeling for our special knowledge about this nearby star. Then I'll put that discussion in the context of the present state and the ultimate fates of all kinds of stars, from very small to very large. We're going to meet some strange characters along the way. White dwarfs, red giants, pulsars, neutron stars, black holes. This is amazing, mind-expanding science. The study of stars leads us inevitably to the conclusion that the universe is a very remarkable place indeed. So first, let's review what we learned about astronomy and the study of stars. In the last lecture, we saw that astronomy is the science and the art of collecting photons. Astronomers measure a variety of characteristics of photons from space. They measure wavelength, which can range from the longest of radio waves to short, energetic gamma rays. They measure intensity, that's the number of photons that reaches us on Earth. We can measure the direction in which the photons arrive. We can measure the polarization of photons and the variation of these parameters with time. Astronomers make these measurements in the hopes that they can learn something about stars. Specifically, astronomers want to know the distance to stars and other objects in space. They want to know the chemical composition of these objects. They want to know the motion of these objects relative to Earth, the temperature, especially the surface temperature of stars, their total energy output, or the brightness, and finally the mass of stars and other objects. Now, astronomers employ a large and an ever-growing array of land and space-based telescopes. They now peruse the heavens in all the wavelengths from radio waves to gamma rays. And as astronomers peer into the heavens, they find that almost everything they see is made of one or more stars. There are countless billions of stars, and they're in the process of being born and living out their lives and dying. Stars can be characterized by their position on this Hertzsprung-Russell diagram. That's a diagram that plots a star's temperature versus its total energy output. The star's temperature is indicated on the bottom axis, that's measured by its color, and the star's energy is measured by a combination of its apparent brightness and its distance. So the Hertzsprung-Russell diagram reveals intriguing patterns in the distribution of stars. A major discovery is that most stars, including our Sun, lie on a prominent diagonal band called the main sequence. You can see that band here, going from cooler, lower energy stars to hotter, highly energetic stars. All of these main sequence stars are now known to be hydrogen-burning stars. The Sun turns out to be a rather ordinary star. It lies right here, right near the middle of the Hertzsprung-Russell diagram on the main sequence. Think about the life of our Sun. Our star can't burn forever. The mass of hydrogen in the Sun is immense, but day by day the mass is diminished. 700 million tons of hydrogen are consumed every second. It's going to take a long time, but the Sun must someday run out of nuclear fuel. Studies of the Sun, combined with observations of the life and death of more distant stars, that reveals that the likely ultimate fate of our own solar system. Because of its proximity to us, the Sun is by far the most thoroughly studied star. Not only can we see it easily, but there are several solar observatories that are dedicated to studying just the Sun. These observatories, including major facilities in New Mexico and in California and in Hawaii, they monitor the Sun continuously during daylight hours. So I want to briefly review some of the information that we've learned about this nearby star. Okay, the Sun is a sphere of hydrogen. It's almost 700,000 kilometers in radius. That's more than 100 times bigger than the Earth's radius. In fact, it's about the radius of the Moon's orbit around the Earth. Now, in cross-section, the Sun has several distinct layers. Most of the energy production by hydrogen burning takes place in the core. That's the central 10% of the Sun's volume. That's where temperature and pressure are the highest, so nuclear fusion can occur. And then energy is transferred from the hot core to the surface, primarily by radiation in the deepest interior. Recall the discussion of the second law of thermodynamics. Heat always moves from hotter to cooler places, and that heat transfer can take place by conduction, or by convection, or by radiation. Now, in the center of the Sun, it turns out that most of the radiation the radiation is the most efficient mechanism. It's turns out that energy moving as photons is the way the heat moves outward. The energy moves 500,000 kilometers in short steps. Now, a photon is emitted and almost immediately absorbed, and then it's emitted again. Now, in the relatively cooler but still extremely hot outer layer, heat transfer is primarily accomplished by convection. This so-called convection layer is 200,000 kilometers thick, and it's a zone of turbulent, hydrogen-rich plasma that forms immense convection cells. So you can imagine the process of heat moving from the inside to the outside of this immense ball, more than 1,000,000 kilometers in diameter. Because of the sun's size, this energy transfer process is calculated to take tens or even hundreds of thousands of years. When we look at the sun, what we're actually seeing is a relatively thin outer layer called the photosphere. The photosphere includes only the outer 150 kilometers or so. This is the zone from which the sun's energy, which took so many thousands of years to travel from the interior to the surface, it escapes into space at the speed of light. It takes 100,000 years to make it to the photosphere, and only 8.5 minutes to cover the 93 million miles to Earth. And then here's the corona. This surface is a violent place with gigantic magnetic storms much larger than the Earth, and unimaginable eruptions of plasma launched hundreds of thousands of kilometers into space. We can't always see this violent aspect of the sun's surface, but the outer regions are suddenly made visible during an eclipse of the sun. During a total eclipse of the sun, the moon passes in front of the sun's disk, and in that brief event we can see the sun's hot glowing atmosphere, the corona, which may extend more than 1,000,000 miles into space. Now, astronomers have developed a special kind of solar observing device called a coronagraph, which blocks the sun disks, and then it reveals the corona even when there's no eclipse. In this way, they can monitor the sun's luminous atmosphere continuously and obtain a much more detailed understanding of the star's dynamic surface. Most of our knowledge about the sun comes from its light energy. That's photons of all wavelengths, from X-rays to radio waves, and they stream to Earth at the speed of light. But astronomers also learn about the sun from its solar wind, which is a constant stream of hydrogen and helium ions that is positively charged atoms, and they stream outward all the time from the sun's surface. This so-called wind is actually extremely tenuous. It's much better a vacuum than can be produced in Earth-based laboratories. But integrated over the vastness of space, the solar wind represents a pretty significant mass. This flux of particles can be measured in outer space and also at the moon's surface. But it turns out that moon rocks collected at the surface by astronauts are impregnated with small amounts of these hydrogen and helium atoms. So when scientists measure these elements in moon rocks, or when space probes detect solar wind directly, they're measuring actual particles that came from the sun. Now, one of the most intriguing aspects of the solar wind is the way it interacts and distorts with the Earth's magnetic field. In this diagram, you can see how the Earth's magnetic field is swept out like the wake of a boat as it orbits the sun. And that's because charged particles like ions in the solar wind interact with magnetic fields like the Earth's magnetic field. The intensity of the solar wind varies. At its peak, it causes the northern lights. That's the colorful glowing of ionized particles. In fact, the effect that produces the northern lights is a lot like the technology of fluorescent light bulbs. In both cases, the gas is partially ionized, and electrons jump from high energy states to lower energy states, and they release visible light photons in the process. Another consequence of the solar wind is that it may from time to time disrupt satellite communications. Magnetic storms on the sun's surface can cause periods of dramatically increased solar wind, and if the solar wind disrupts the Earth's ionosphere, the atmosphere may not scatter radio waves very efficiently. My dad's an amateur radio operator, and he talks about days when the sun is well behaved and then days when the sun isn't so well behaved. Well, now that we've seen some of the distinctive characteristics of our own star, we can return to that more general question of the lives of other kinds of stars. It's our intimate knowledge of the sun combined with telescope observations of countless other stars that allows us to model the life cycles of different sized stars. Now, models reveal that the lives of stars are a constant battle. It's a battle between the force of gravity that pulls inward on every particle of mass, and then that radiative force of nuclear fusion pushing outward like nuclear explosions. For a star like the sun to be stable, these two epic forces have to be more or less in balance. So the unimaginable gravitational force of all that hydrogen is matched by the nuclear reactions going on in the sun's core. Indeed, these two forces must be balanced for any star to be stable. Throughout the lifetimes of stars, the two forces play off against each other. They're computer models of the sun and other stars, and they're extremely complex. Stars are modeled with a series of mathematical equations that describe lots of concentric shells of matter at different temperatures and pressures. And then these models compute the total energy output from each shell, the changing composition of each shell, energy transfer from one shell to another shell, and so forth. In order to constrain models of this type, astrophysicists have to merge information from nuclear physics about hydrogen fusion and from plasma physics about the density and dynamics of hydrogen plasma. They use fluid dynamics about convection in plasma. They need cosmochemistry about the details of the composition of younger and then older stars, and lots more. So Earth-based measurements of the sun's size and its mass, its surface temperature, its energy output, those are also extremely important constraints to these models. After all, any model has to duplicate the behavior we see in our own star. So to model a star, modelers estimate a starting temperature, a pressure, a composition for each of those concentric layers, and they assume that the first law of thermodynamics holds for every layer. Energy has to be conserved. Then the model predicts how temperature, pressure, composition change layer by layer over time. The evolution of the outermost layers, for example, determines how much radiant energy comes to the Earth. The major conclusion of several of these models are now in close agreement. 4.5 billion years ago, when the sun formed, it was less bright, perhaps only 70% of its present energy output. In fact, over most of its lifetime, the sun has gradually been getting a little bit brighter, and for a time it will continue to be getting slightly brighter. This relative change in the sun's intensity leads to what has been called the early faint sun paradox, about which we're going to hear more in Lecture 54. In brief, the sun was too weak to maintain a liquid ocean on the early Earth, at least with the atmosphere as we now know it. So the sun's energy output very gradually increased, and it continues to do so, although not noticeably in many, many human lifetimes. So modelers estimate that the sun will continue its hydrogen burning stage for several billion more years. Over time, the sun changes. But perhaps the most significant aspect of these star models is how constant the sun has shown and will continue to shine for so many billions of years. There are no big flare-ups or sudden drops in solar output. This is basically true of all the stars that lie on the main sequence. Hydrogen burning is a pretty steady process. Now, most stars spend most of their lives burning hydrogen. The sun has stayed on this main sequence for most of its 4.5 billion years, and it will remain there for billions of more years. And that's true for most other stars as well. But there are other kinds of stars that lie significantly off the main sequence. It turns out that those stars tell an amazing story that reveals the ultimate fate of our own sun. Look at the Hertzsprung-Russell diagram. Red giant stars up here, they're relatively cold stars that give off lots of energy. That means that the stars had to be big. The only way a cool star can give off a lot of energy is if it's big. And then over here, white dwarf stars, which are relatively hot but don't give off very much energy. The only way a very hot star can give off very little energy is if it's small, hence white dwarf. These kinds of stars suggest that other processes besides hydrogen burning are eventually going to come into play. You see, all the hydrogen-burning stars, from relatively small to relatively massive, lie along the main sequence. Stars that lie elsewhere in the Hertzsprung-Russell diagram must get their energy from some other source. Now, throughout this discussion, it's essential to remember that the star stability depends on the balance between gravity pulling in and radiation pushing out. All stars eventually run low on hydrogen fuel in their cores. You can't consume prodigious amounts of hydrogen in fusion reactions forever. So what happens then? In the final stages of a sun's life, helium concentrations are going to build up in the core, and hydrogen burning can't occur there. So next, hydrogen burning takes place farther out in shells progressively closer to the sun's surface. As the hydrogen burning gradually moves closer to the sun's surface, it'll cause the sun gradually to expand outward because there's less gravity to counter the outward pressure created by these nuclear reactions. So here's the sun with nuclear reactions occurring closer to the surface, and it starts to balloon outward. And as it does so, it soon engulfs the innermost planet Mercury. Mercury is going to be vaporized as the sun's corona moves outward, and the sun will keep getting larger. Eventually, its diameter will exceed the orbit of Venus, though it turns out that Venus won't be swallowed up. You see, according to astrophysical calculations, and I should tell you, everything I'm telling you here is based on calculations. The swollen sun is going to have a vastly stronger solar wind, and the actual mass of the sun is going to decrease sufficiently so the orbit of Venus moves outward as the sun expands. All the other planets are going to move outward as the sun expands too. And if the sun's mass is less, the force of gravity holding the planets is also less. That's why the orbits get larger. At some point during this dramatic transition, the Earth is going to become uninhabitable. The sun's going to expand to many times its present radius, so the total radiation from the sun reaching the Earth's surface is going to increase dramatically. The surface temperature of the Earth will rise. The oceans are going to boil off. Life on Earth is going to cease. But I don't want you to lose too much sleep. All this isn't going to occur for perhaps another 2 or perhaps 3 billion years. Now, think about how these events predicted for the sun's future would look on a Hertzsprung-Russell diagram. Here's a plot of the sun's life. The sun starts and lives most of its life on the main sequence here. But once the long period of hydrogen burning in the core ends, the sun leaves the main sequence. The sun begins to emit much more energy than it does now, but it'll do so out of a much larger and growing surface area. So the surface, therefore, will actually become somewhat cooler, and the sun will become a red giant. It's going to reach its maximum size perhaps 3 billion years from now. Note this process takes the sun away from the main sequence towards the upper right of the Hertzsprung-Russell diagram. As a result of the hydrogen burning around the core gets hotter. It's sort of like the same effect you get in an oven. That increased temperature and pressure causes all the remaining hydrogen to be consumed, and then a new nuclear fusion process starts. Look at this. Hydrogen has been transformed to helium, which itself becomes a nuclear fuel. Helium nuclei fuse to form heavier nuclei, notably 3 helium-4 nuclei eventually become a carbon-12 nucleus in the process called helium burning. For a sun-sized star, carbon is as far as fusion reactions in the core can progress. Hydrogen element 1 burns to helium element 2. Then the helium fuses with itself to make beryllium, that's element 4. That fuses with more helium to make carbon, element 6. Once the core of the sun becomes carbon, the nuclear processes in the core slow down. It's as if you had a fire in the fireplace and all the wood burns up. You're left with a pile of hot, glowing coals. Again, you can follow the progress of the sun on the Hertzsprung-Russell diagram. So the sun lies near the main sequence for billions of years as hydrogen burns in the core. Then you have hydrogen burning in the outer layers and gradual expansion. The sun produces more energy, but its surface becomes cooler due to the expansion. Then there's a relatively short period of helium burning during the red giant stage. And finally, when helium burning ends, the outward pushing radiation pressure is turned off, and the star begins to collapse under gravity. See, there's no longer a significant outward pressure, so gravity wins. Smaller and smaller the sun's going to become, eventually shrinking to a dense sphere about the size of the Earth. The sun will become an incredibly dense ball of carbon, thousands of times denser than diamond. Think about the energy of this process. Nuclear fusion is no longer taking place, but the mere process of gravitational collapse requires the conversion of unimaginable amounts of gravitational potential energy into heat. So the tiny star becomes very hot. It's an object the size of the Earth, glowing with a surface temperature of tens of thousands of degrees. It's a white dwarf. And that's over here on the Hertzsprung-Russell diagram. Eventually, the total energy output of the tiny cooling sun will be only 1,000th of its present value, but the sun will glow brilliantly because of the high surface temperature of tens of thousands of degrees. Slowly, the sun's going to cool as that residual energy floods out into space. The second law of thermodynamics has to apply to stars. Heat flows spontaneously from warmer to cooler objects, so the heat from the glowing sun will radiate out into space. Okay, I've told you an intriguing story about the sun. But what observational evidence do we have that it's remotely true? Is this just some astrophysical fairy tale? Well, it turns out you can watch every stage of the sun's predicted future in telescopes. See, what's plotted on the Hertzsprung-Russell diagram are all different kinds of stars that can be observed in the heavens. We see sun-like stars. We see red giants and white dwarfs. We see every step in the sun's life, past, present, future. We find that our sun is a rather ordinary star, like literally billions of other stars in the heavens. And we could watch those other stars and see a time-lapse picture of our own star's fate. And now at last, we're ready to examine different sizes of stars and see their ultimate fates. The smallest stars, those are ones about 1/10 the size of the sun, are called brown dwarfs. And think about what a star like that must be like. These small stars burn their hydrogen very slowly, unless they never get very hot or very large. These brown dwarf stars lie on the main sequence since they do burn hydrogen, but they're found at the extreme lower right corner. These stars are both very cool and they produce relatively little energy. Brown dwarfs never get beyond hydrogen burning. There's not enough gravitational pressure, nor is there a high enough temperature to start helium burning. In fact, brown dwarfs burn their hydrogen so slowly that they continue to glow weakly for perhaps 100 billion years. Because brown dwarfs are so faint, they're extremely difficult to detect with ground-based telescopes. Astronomers have had a lot better luck using orbiting infrared satellites, and they look for hot objects in space. Relatively nearby brown dwarf stars have been detected in this way. The number of documented brown dwarfs has been growing very, very rapidly also. It now appears that such stars are common, though we won't be able to see them unless they're pretty close to our own solar system. And then stars more than a few times more massive than the Sun experience a very different fate than the sequence of red giant and white dwarf that we've seen for the Sun. Look at this cross-section. Larger stars are going to have several concentric layers of fusion reactions. Going deeper, you first find hydrogen burning in a shell that produces helium-4. Then helium burning in a shell that produces carbon-12. A star 10 times more massive than the Sun will burn its hydrogen fuel in perhaps 100 million years. That's a small fraction of the Sun's lifetime. Note that the larger the star, the faster it burns, and the shorter its life. Hydrogen burning in these more massive stars is followed by the much more rapid production of progressively heavier elements. Look at this. Oxygen-16. Neon-20, magnesium-24, and so forth, all the way up to iron-56. The last of these nuclear fusion steps can occur in literally a matter of minutes. So the star produces energy through fusion reactions all the way to iron-56. But recall from the lecture on nuclear reactions the special nature of iron-56. Isotopes less massive than iron-56 can generally release energy through nuclear fusion reactions. So two hydrogen atoms fuse to form a less massive helium atom plus energy. Isotopes heavier than iron-56 usually can release energy through nuclear fission reactions. The heavier atom splits into two pieces with slightly less mass again, plus energy. But iron-56 is different. It's the ultimate nuclear ash. Under no conditions can nuclear energy be extracted from iron-56, either by fission or by fusion. When a star races through its final fusion stages to iron, nuclear fires suddenly turn off. In an instant, the nuclear force that's countered the immense pull of gravity for millions of years is turned off. It's like pulling the rug out from under the star. Faster and faster, the star literally implodes. In an instant, the star collapses to form an inconceivably hot and dense mass. In that instant, like a jumper on a trampoline, the star then rebounds in an explosion of unimaginable power. Such an exploding star is called a supernova. In that maelstrom of heat and light, all sorts of atomic nuclei are forced together, and they fuse in new ways. Nuclei of all sizes are fused together to form every element of the periodic table. Indeed, every element more massive than iron is formed at that instant in the exploding star. Think about that. Under normal circumstances, stars begin mostly with hydrogen. Over millions or billions of years, that hydrogen is gradually fused to heavier elements, helium, carbon, oxygen, and so forth, up to iron, which is element 26. That's it for normal processes. Fusion can't take you any farther because no more energy is produced. But when a star explodes, all the immense extra energy forces nuclei into new massive collections of protons and neutrons, including all the more massive elements. Every atom of lead in your cut glass, every atom of silver in your silverware, every atom of iodine in iodized salt that was synthesized in an instant in an exploding star more than 4.5 billion years ago. A supernova is the only known natural process to make all elements more massive than iron, which is element 26. Next time you hold a piece of gold jewelry, a gold wedding band in your hand, think about that. All the atoms of gold came from exploding stars in deep space. This is an astonishing vision, but it's the way the universe works. This is what Carl Sagan meant when he said, "We are all made of star stuff." When a star explodes, these diverse atoms, they're flung far out into space in all directions. They seed the galaxy with raw material for future stars. We can actually watch this happen. Dramatic telescope photographs, many of them taken by the Hubble Space Telescope, show the remnants expanding of supernovas, flinging new supplies of all the chemical elements into space. Here's a picture of one of these events. This is supernova 1987A, which was observed to explode in 1987 in the southern hemisphere. Astronomers now have more than a decade worth of pictures of this explosion. In the coming years, I expect that they'll be able to put together a time-lapse movie of the event. You can actually see the ring-like shockwave of the explosion racing out from the center here. Now, the fate of any star a few times larger than the sun is to explode. That's the supernova. But usually when a star explodes, it leaves behind a smaller, but nevertheless quite massive object that marks the place of the former star. And these remnants are among the most bizarre objects in the universe. So I want to tell you about three variants called neutron stars, pulsars, and black holes. Here's an artist's sketch of a neutron star. Any leftover mass more than several times that of the sun will collapse into an incredibly dense object in which atoms are no longer stable. Gravity is so strong that electrons and protons are crushed together and they merge to form neutrons. Okay, that's just the reverse of beta decay. Recall that in beta decay, a neutron splits into a proton and an electron. This is the opposite. A proton and electron become a neutron. Such a neutron star might be only 10 miles in diameter with a mass several times that of the sun. That's an object the size of a small city with a mass 3 or 4 suns. You can't really imagine what such a place would be like. Neutron stars rotate extremely rapidly. That's because every star has some rotation, and as it collapses down, it's like it spins faster and faster. That's like an ice skater pulling in her arms as she spins much faster. So neutron stars spin rapidly. Another aspect of neutron stars is that they have very, very strong magnetic fields that generate powerful radio waves as the star rotates. Look at this. From Earth, these radio sources may seem to pulsate thousands of times per second if the star is properly oriented. Such a pulsing radio source is called a pulsar. And when they were discovered in 1967, these so-called pulsars were at first mistaken for a possible sign of alien life. The regularity of the pulses suggested a technological source, though the true nature as a rotating star was soon deduced. Nevertheless, pulsars are given star catalog designations of LGM. It stands for, believe it or not, little green men. Astronomers do have a sense of humor. And if neutron stars and pulsars aren't strange enough, there are black holes. If the leftover mass after a supernova explosion is more than about 30 times the mass of the sun, then that mass will have such immense gravitational force that even neutrons are unstable. The neutrons, in effect, disappear, and all the mass collapses down into a point called a black hole. Nothing, not even light, can escape from a black hole. Gravity takes over completely. Indeed, a black hole represents the ultimate victory of gravity over the other forces of nature. Here's an artist's concept of a black hole. While black holes themselves are invisible, it is possible to detect black holes indirectly. For one thing, if a black hole is in a binary star system, it's often possible to see matter from the adjacent star streaming into the black hole. These very energetic transfers of matter produce lots of electromagnetic radiation because charged particles are accelerating from the star into the black hole. Black holes may also be revealed when they act as gravitational lenses. A gravitational lens is a massive object that bends light coming from more distant objects. This was a prediction of Albert Einstein's general theory of relativity and has been amply borne out by many observations. A distant star galaxy will appear to be distorted as the result of an intervening black hole, so even if you can't see the actual black hole, you can tell it's there. And there's a third way to detect extremely massive black holes. Objects with mass of thousands or millions of stars are sometimes supermassive black holes, and they give dynamic effects. Galactic astronomers suspect that such massive objects exist near the centers of many galaxies, including our own Milky Way galaxy. See, astronomers observe that many stars near the center of the Milky Way are moving much, much too fast. And the most plausible explanation is some supermassive yet invisible object, a supermassive black hole, around which the stars are rapidly orbiting. I want to conclude by pointing out that much, if not most, of what I've told you in this lecture has been discovered in the past few decades. We live in a golden age of astronomy, and the discoveries are going to keep coming. Thanks to the internet and the efforts of the astronomical community, you can share in these amazing transforming discoveries almost as they happen. Well, in summary, our studies of the sun and other stars reveal that the ultimate fate of stars depends on their mass. Stars that are much smaller than the sun are brown dwarfs. They're destined to sort of fitfully fuse small amounts of hydrogen to helium for perhaps hundreds of billions of years. Stars the size of the Sun enjoy billions of years of stable hydrogen burning, but they eventually exhaust their core supply of fuel. They expand relatively briefly to an energetic red giant star and then collapse to a dying white dwarf. And stars much larger than the Sun, they end their lives in giant supernova explosion. They litter the galaxy with a fresh stock of elements from which to build more stars. And the massive remnants of those explosions include neutron stars and black holes. In the next lecture, I'll continue our exploration of stars by considering the vast collections of billions of stars called galaxies.